In this video, I will cover the grounding point of view, the basically the transformers neutral grounding in a power system network for different voltage levels, starting from LV 415 volt up to 132 kV or 400 kV EHV systems. So I will cover sometimes it will be theoretical part and why it is required and different types of grounding, and with the help of ETAP software also I will try to simulate the three-phase and single line to ground fault also, and there will be some discussion points related to this single line to ground fault and the comparison with the three-phase faults, and some of the case studies I will discuss in detail. So maybe a little bit lengthy video, but it will, I believe this video will be helpful for the engineering professionals to understand the grounding, the neutral grounding of the transformers, or maybe for the generators in a power system network. So let's start from the low voltage side. Coming to the 415 volt low voltage system, here is the downstream network. Actually I am using the same network whatever I have used in my previous some of the videos. So for the relay setting purpose also I have used this network. That's why the relays and connected cities are also configured here. Okay, so today's point of discussion related only to the grounding perspective. So this is the distribution transformer. As you can see, this is a 2 MVA distribution transformer stepping down from 6.6 kV to 415 volt voltage level. So let's check here under this grounding tab. If we check this box symbols, then it will show the grounding symbol, and here we can select whether it is solidly grounded, or it is resistance grounded or reactance grounded. So different grounding configurations are those are available in ETAP software. So we'll select the solidly grounding system for low voltage system. Why? The question is why? Because for low voltage system, for 415 volt system, as per the regulation, those should be the solidly grounded system. We should not use the resistance grounding system. So if we use the resistance in between these two, if we use the resistance, suppose this is resistance. So if we want to limit let's say 10 ampere ground fault current, if we want to limit this one, the main problem is that it will be very difficult to sense the ground fault current, because this will be too much, so it will be difficult to sense the ground fault, this sensitive ground fault. So this is not recommended for low voltage system. And for 6.6 kV system, suppose lot of motors are connected, as per the process requirement. Different rated motors are connected with this system. So if we allow this ground fault current in this voltage level, 6.6 kV or 11 kV voltage level, in that case the motor stator core may get damaged. And here we can use for this transformer, for this 33 by 6.6 kV step down transformer, we can use the resistive grounding system. So this is the resistive grounding system. So this is suppose this grounding system will be this grounding current will be limited to 300 ampere. So it is 300 ampere resistance ground system. Accordingly, this resistance ohm, the value of ohm, this will be calculated based on that requirement definitely. So this in NGR neutral grounding resistor will be connected for these two transformers, and here for the 33 kV system also sometimes we can use the inductive that impedance grounding system, or definitely this is not solidly grounded system, or also a reactor or resistor we can use. Let's say this is 400 amps. This fault current will be limited to 400 amps. So you can use 400 amps. Similarly here also for this transformer, let's say this is resistance grounded and 400 amps. Okay, okay, okay. Oh, one more important thing, I want to share here. Suppose for 6.6 kV system in this switchboard, in bus A or bus B, there is no motor connected with this bus. So in that case, as per the code or the standard, we can go for the solidly grounded system also. But if there are motors connected in this 6.6 kV system to protect the to protect the motor stator damage, to avoid the stator damage, core damage, we have to we have to limit the ground fault current. So in that case, we have to use the resistance or reactance grounding system. Preferably it is resistance grounding system. So we have to use this NGR or neutral grounding resistor. Okay, now quickly we'll jump to the simulation, this short circuit analysis using the ETAP software. Let's see what are the impacts in three phase ground fault or single line to ground fault with the help of this simulation software. Okay, so this is AC max case. So over here is the standard. Here is the max, and the C factor is considered for LV system. This is 1.05, and for high voltage or extra high voltage system, this is 1.1. This C factor also, it can be user defined. C factor. In that case, you can change these values as per the specification or as per the regulation. But this is the maximum condition. This is the C factor. You cannot edit here for this. So we are using this maximum, and this is dual feed configuration. So let's run this. So this is for the device three phase device duty. So we'll not run this one. We'll run this 60909. The 60909 IEC 60909. This is for three phase fault, three phase and single line to ground fault, line to line, and LSG, line to ground fault as well. So let's run this one. Okay, it's fine. So this is coming. This is what it is showing, that this is 22.115 kiloamps, 22 kiloamps. So what is this? This is the three phase fault. This is three phase faults. Okay, let's select single line to ground fault. What are the values? Okay, for the single line to ground fault, here you can see we have limited this NGR, this neutral ground fault current to 400 amps. So this is coming 413 amps, 413 amps, whereas we have limited to 400 amps. So this is coming because of the C factors. Because of the C factor, what we have used in the short circuit study case editor. Here, as per the standard, you can see this is the C factor for less than 1 kV, 1.05, and for this greater than 1 kV and less than 230 kV, this is 1.1. So because of this C factor, this is coming more than 400 amps. This is 413 amps exactly it is coming. And here at the 6.6 kV voltage level, we have limited this to 300 amps, and here it is coming 314 amps, because of, again, this is because of the C factor. So this is restricted to 314 amps. So with the help of the suitable higher sensitive relay, we can detect this ground fault current of 300 amps. Okay, so let's check for the LV system as well at 415 volt level. At 415 volt level, as you can see here, this is 40.793 kiloamps. This is 40.793 kiloamps, and for bus B, it is 39. This is 39.64 volt, so almost 40 kiloamps, for bus A and bus B. Why? Because of the solidly grounding system in this transformer. This neutral is solidly grounded, so that's why the fault currents for the single line to ground fault, this fault current is not limiting, nothing is limiting. So this is the solid connection between this transformer neutral, and the ground. So that's why this is coming 40 almost for 40 kiloamps. And interestingly, there is a high chance that this single line to this this single line to ground fault values approximately 40 kiloamps, maybe higher than the three phase current itself. Let's check what is the value of three phase. Select here three phase current. Let's check. You can see this is 38.219 kiloamps, and here 36.717 kiloamps. So the three phase fault current is lower than single line to ground fault current, because if we go back to line to ground fault current, you can see this is much more, this value is much more because of the solidly grounded system. And this is very easy actually. This should be easier to detect the fault current, to detect the ground fault, because of the higher value of ground fault current. So it will be easier to detect the ground fault current. But for 6.6 kV system or 11 kV or 33 kV system, we can use separate sensitive relay with the CT, dedicated CT, to measure this fault current. Suppose okay, now if we talk about the extra high voltage system, let's say at 400 volt or 765 kV system, there again it will be solidly grounded system. We should not use the resistance or reactance grounding system at EHV level, that means 400 kV system level, because at 400 kV system level, if it is the solidly grounded system, and the fault current, that neutral that grounding fault current will be higher, and there the relay, the protective relay will trip within 3 to 4 cycles, 3 to 4 cycles, that breaker will trip. Actually the fault will be cleared. That means within 200 millisecond, 180 to 200 millisecond, the fault will be cleared instantly. So that instantaneous setting will be there actually. So the fault will be cleared instantaneously. So there the solidity grounding system can be used. We should not use any resistance or reactive grounding system. So how, let's model that one. How we can use, here it is. Suppose if this relay is being used for the 400 for 400 kV system, this instantaneous element, this is instantaneous element 50 element for overcurrent relay. So it will trip that relay instantaneously. Actually, suppose this is point 0.02. So this is the minimum range actually. This is the minimum is 0.015. So we are considering 0.02 millisecond, that means 20 millisecond. There is no intentional time delay, so instantaneously that will be tripped. So we can use the solidly grounding system at 400 kV voltage level. So these are the brief, and also I have shown with the help of this simulation software. So the main thing we need to keep in mind whenever we are talking about the grounding system, the LV system should be solidly grounded. Medium voltage system should be grounded with the help of resistance or reactance, and extra high voltage system should be grounded solidly or effectively. There should not be any resistance, or there should not be any impedance in between the neutral and ground. Okay, one more case study I want to show you here for the LV network. For the LV network, if we once again, if we run this 60909, okay, so this is the, I think this is single line to ground fault. Okay, now if we change, just to do an experiment, here, if we choose the resistive grounding system, let's say it is limited, this ground fault current is limited to 10 amps. So let's select this. So now this resistance is now added here. Okay, now let's run this one. So it was 40 kiloamps. So now this is 10 kiloamps. This is 10 kiloamps. This is 10 kiloamps. Sorry, this is 10 amps only. Sorry, this is 10 amps only, because this is limited to 10 amps. But the main challenge here for the LV system, if we use this resistance in the neutral grounding system, then in that case it will be very difficult to sense this fault current as much low as this 10 ampere. So this is very challenging. And also, as per the course, as per the international course also, we should not use any resistance or reactance for the neutral grounding for LV system. We should always go for the solidly grounded system, so that it will be very easy to detect the location and the current, this ground fault current, and it will be very easier to isolate, to trip this protective device to isolate, to clear the fault instantaneously. because this LV system is being used in all the commercial as well as the domestic purposes also. So most of the cases it is found that the LV system is very close to the unskilled or the common people also. So in the domestic purpose also, we as a common human being, we are also going to operate this board. So that will be very risky, as well. So this LV system should be solidly grounded as per the codes as well. But for the medium voltage system, it will be resistance or reactive grounded system. And for extra high voltage system, suppose 400 kV level, it should be again solidly grounded system. So up to this, I think there is some value addition. And if there is any question, I know there will be a lot of questions regarding this grounding and grounding or earthing. Though these terms, though these are the different terms, but basically grounding and earthing, those are the same thing as per the international standards. And if we talk about any publications also, regulation, there also this grounding and earthing, basically this is the same thing. There is no difference, there is no technical difference between grounding and earthing. So if there is any question, just let me know, and I will come back to you for the theoretical part. Okay, thanks.